Okay. So, in the last class we discussed Fourier space representation. So, we did definitions, then we looked at the Navier-Stokes equation in Fourier space, then energy. Okay. So, I covered that in the last class. So, now we go and derive equations for vorticity, kinetic helicity and entropy. So, that is what we will do today. So, vorticity in real space, this is the definition. No? So, vorticity is a vector curl of u. So, vorticity vector is curl of u. So, I mean bold means vector anyway. So, now what happens in Fourier space? So, curl is a derivative operation, but in specific way, but it is all derivative operation. So, you can easily show, now this I will not do it here, but it is just that this grad gives you k, but this curl, so k is vector. So, it is basically I k cross. Okay. So, this I will not derive it, but straightforward you can just do it yourself. Okay. Now, from this, so this is given u, I can compute omega. So, please remember there is a wave number k, the wave number k, so k wave, and there is a velocity field. By definition, it is perpendicular to k in a plane. So, this is u of k. So, it could be anywhere in the plane perpendicular to k is in 3D. So, omega is also a vector which will be obtained by taking the cross product of these, which will again k cross u k. So, we can just do it, it will be in the same plane. Now, I can compute from this relation I can compute u of k. How do I do it? Which is useful. So, I will need this information. So, I can compute u of k very easily. So, just multiply, take a cross product of this equation. So, I take a cross, so I will give minus, and then we have k cross u of k. So, I am doing some of it as just for you to get familiarized. Now, what is this A cross B cross C? So, this is B C dot A. So, k dot u k, there is a minus sign here, minus C A dot B, right. So, minus minus becomes plus, so that becomes u k k squared, A dot B is k squared, but k dot u k is 0, incompressibility. So, this is gone. So, we can get u of k easily from here, u of k, in fact I have it in the next equation, u of k is I by k squared k cross omega k. Okay. We need this in our later derivations. So, is that clear? So, vorticity is an important quantity which we can write in Fourier space as well. So, next is equation for the vorticity. So, we start always with real space equation. So, this equation in real space which I derived it, so omega is very similar to magnetic field equation, and this omega f omega is curl of f of u. So, f u is the force for the velocity field. So, f omega will be take the curl and you get f of u, f of omega. Now, this has been done before. Now, I can convert this to Fourier space. So, how does it look like? So, I mean this we have done it before. So, I will not go to every step, but we just so this vector f of omega becomes f omega k, this grad becomes minus k squared, grad square becomes minus k squared, this was this one. Now, this one omega d by dt of omega becomes d by dt of omega k. Okay. Now, this is partial derivative here and this is total derivative, because k is a number. So, this is all of them are function of t, dynamic the function of t. So, is function of t, that is why I am doing total derivative. K is a number, k we are not, k is a wave number, is fixed. Now, we need to worry about what is n omega or Fourier transform of this. So, it is easy. So, curl gives you I k cross. So, this one is I k cross, and the product, in fact is a cross product, but is a product, but in specific way, ux omega y and so on. So, this product becomes a convolution. So, this is a convolution with understanding that q equal to k minus p. Okay, this we did in the last class. So, this is equation for n omega. So, it is a convolution, it is not just a product of u and omegas. Now, this can again be simplified, this one, using A cross B cross C. So, if I do it following the same logic, then I get n omega as k dot omega q, this one, and u q, and k dot u q omega p. Okay. So, there are two terms. So, this object has two terms here. First term is, okay, I must tell you that this sum has this. So, this minus sign is inside the sum. Okay. So, if I just substitute it there, what will I get? So, minus becomes plus. So, if I substitute, I just want to tell you about the structure in another way. So, I will get I k dot u q omega p, this minus becomes plus, this minus is minus k dot omega q u of, I am sorry, I made a mistake here, no, this is u of p, this I is sitting here. Okay. So, these terms I will explain in more detail, and they mean something. This is has this sum. These terms have very specific meaning, and they have very specific role in energy transfers and dynamics. Okay. But these derivations, straightforward, but you do not need to memorize it, but you should know where to look for, and after some time hopefully it will become part of you. So, you should be able to easily construct this stuff. Okay. This for vorticity. So, we need this equation later, and we consider dynamics of vorticity and how modes interact. Now, kinetic helicity. So, this is what we did in real space. So, there were some questions, how do you visualize helicity, So, let us see this in Fourier space. So, remember it was in real space, I should have written in real space, it was u dot omega half, that is hk. Now, in Fourier space, what will that be? So, it is a product. So, product becomes again a product in Fourier space, but one of them is a complex conjugate. So, I took lot of pain to show you that one of them must be complex conjugate. So, I put a complex conjugate here, or you could have put complex conjugate in omega, no problem, but one of them must be complex conjugate. If you do not, then that is not correct. Okay. So, again reminding you that either I could have put this as omega star of k, no problem, because a star b real part is same as a dot a b star real part. Okay. That is simple stuff. I could have used this as well, the real part of this. So, this means real, no? This means real. Now, there is a nice derivation that this quantity in the left equals to this. So, Re means real part of u and imaginary means imaginary part of u, cross product of the real and imaginary. So, you need both real and imaginary, and they should not be aligned, real and imaginary. They should be perpendicular, well, there should be some angle between the two. Then you will get non-zero helicity, non-zero kinetic helicity. Now, let me just go through the proof. It is quite straightforward, but just for completeness, let us do the proof. So, how do I do this? Half real. So, omega k dot u star of k. Okay, just my algebra becomes slightly better. Half real, omega k, these are our vectors. Okay. So, omega k is I k cross u of k dot u star of k, right. I just put that. Now, what about a cross b dot c? So, these are vectors, right. So, what is that A cross B dot C is A dot B cross C, we can rewrite it. So, I am going to rewrite this as I inside K dot bracket U K cross U star of K. Now, see, if the star was not there, U K cross U K will be 0, but U K cross U star K is not 0, need not be 0, it could be 0, but it need not be 0. So, now we can rewrite them as real and imaginary part. Half real I K dot, now this is what is bit of U real. So, I am just going to write R plus I U imaginary I cross U real minus, right, I mean by the way this is real, U real is real, U imaginary is also a real number, a real vector, these are vectors. Now, this real, now I take the complex conjugate of the same thing, minus I U imaginary of, to save time I am not writing K inside, but the argument is K. Now, what is this object? U real cross U real is 0, U imaginary cross U imaginary is 0. So, you just do this algebra, then there I will come, and if you just carry forward this one, you will get the desired quantity or desired result. This K dot U real cross U imaginary. I mean, it is quite easy to see. This real I do dot product with this, a cross product with this for non-zero, and this one with that, and they are equal and opposite. So, that is what happens. Okay. So, this is a real number. Okay. I do not need to take real because it is real. Now, you can immediately see that both real and imaginary part must be non-zero. So, just to connect with what you already know, that for linearly polarized waves, electrodynamics, so linearly polarized wave, U of k, it can be written as, so you can write this as linearly polarized. So, the vector is along a plane, no, this is a along plane, electric field is along a plane. So, but it could be complex. So, Fourier transforms are complex numbers. So, real and imaginary part are in the same direction. So, if I take the real part and imaginary part, so this is U is a vector, but they are in the same direction. So, cross product will be 0. So, linearly polarized waves have 0 cross helicity. However, so is that clear? I mean, this is straightforward, no? Now, however, what is, so I will erase this. If you have circularly polarized waves, so normally you represent like this. So, we have real part U real. So, it has two parts. So, you write sine and cosine, right. If you remember, it is written as A cos kx minus omega t x cap plus B y cap sine kx minus omega t. If you recall your, this is how you, this is a wave travelling, no, actually not along x is z. So, this is a wave travelling along z direction with polarization with x and y, I mean it has component along both in x and y. If I do the Fourier transform of this, I will get one of them is real, right. So, if you do the Fourier transform, so this I will in fact I will give as a homework. So, you do the Fourier transform of this object, then you will find that this velocity vector or electric field vector U vector has both real part and imaginary part, but they are not in the same direction. So, just to get a feel for it, so this will be A by I, no A by, this is A by 2, no, cos is the Fourier space will be by 2, and this will be B by 2 I, and B by 2 I is along y direction, but A by 2 is along x direction. So, that is why the cross product will become non-zero. So, this is the example of a field which has non-zero cross helicity, okay, and this is in fact very compact formula, okay, I mean this is a really nice formula and you can apply anywhere. So, this is just this is u real and u imaginaries are real numbers, real vectors in fact. So, take a cross product, there will be a real vector and k is real. So, this whole thing is real. So, this I and multiplied by this I gives you minus 1. So, real part of real is real. Okay. So, it is by not, I didn't push, I didn't make any approximation, it is just real, and it better be, this is real, this is real and this is real. So, it should be real. Okay. So, this step I missed, I didn't explicitly do it, but you can just do it. Okay. So, this is a intuition for cross helicity, kinetic helicity, and we will come back to this again. Okay. So, I am going to do this in fact tomorrow's class. We will look at cross helicity, kinetic helicity, in other words, kinetic helicity again in another basis. But I presume that this circular polarized wave, you are getting the idea. So, this is exactly a by 2 and this is b by 2 by I, and that gives you non-zero value. Okay. Now, we can derive. So, okay, so now we can make some statement about maximal helicity. In fact, that was one of the questions. So, when is this guy maximum? So, there is a k vector, and I know that u real and u imaginary must be perpendicular to k. So, u has to be perpendicular. So, these u real and u imaginary lie in this plane, and you can immediately see that in 2D you cannot have any cross helicity. Again why I am saying cross helicity, kinetic helicity, because u real and u imaginary will be along the same line, it is like plane polarized wave. But Hk, so when is this maximum? When u real and u imaginary are perpendicular to each other, then this is maximum. So, it is maximal when u real are perpendicular to each other. So, the examples which I had constructed before, which I showed in one of the earlier classes, u real and u imaginary were perpendicular, and that is why it was maximal helicity. Okay. So, the product will be mod of this u real, u imaginary, k, angle between the two, which is sin alpha, which is angle between the two. No. So, alpha must be 90 degrees for maximal value. Now, this can be negative or positive, this cross helicity. Again, kinetic helicity could be either negative or positive, and that depends on the sign of this. Okay. So, we can get both maximal and minimal when they are 90 degrees to each other, just appropriate phase. And the examples we will again revisit today in Fourier space, and you can see that y should be positive, maximally positive or maximally negative. Okay, now we look at the equations. So, this is what I wrote, no, this is a formula. Now, we replace this u. So, in fact, I need to do the by formula I derived in the second slide or first slide of this. So, the uk is replaced by, so I remember k cross omega k divided by k squared I. So, dot omega star k. So, what do I do? A cross b dot c is a b cross c. So, this b cross c and a dot product. So, we write like this. Now, using that equation, so since I have omega and omega cross, so this is convenient. So, these are all there in the notes, you can just look at all this derivation. So, then you just take d by dt of this. So, there are two of them now, omega and omega star. So, there will be two derivatives by product rule, there omega this d dot means d by dt. So, first d by dt will act on this one and second d by dt will act on this, and as a result, now what is omega dot? I derived some time back. So, which is convolution. No? So, the nonlinear term. So, the other part which is going to come in a minute. So, this is coming from the force part and this is the viscous part. Now, this derivation I will not do it, in fact this bit clumsy is no doubt, but the nonlinear part which we should focus on. So, omega dot is, so this has to be replaced again by k cross u cross omega convolution. So, there is a convolution here, no, u q omega p. Now, if I put subscript, that means it's a wave number. Okay. Now, that is what has come here, omega p and u q, and this k cancels, k squared, there is 1 k here and 1 k here and there is k squared below. So, k squared gets cancelled. So, this is kind of nice trick which gives you this formula u q omega cross omega. Okay. So, this is the formula for this, and which we will need it later. In fact, this was what we did in IIT Kanpur when our visitor from France had come, this is. So, this simplifies a bit, and Frank Plunian, I think he kind of gave this form. Well, this is known before, but it's nice to do them, this nice form. Okay. Now, just to contrast d by dt of what about, now I am sure you won't remember now, but what about kinetic energy, nonlinear term, how did it look like? So, that has the form k dot u q u p dot u star of k, all vectors, and this sum over p's. It is of this form. So, there is a dot product of two Fourier modes and wave number with the Fourier mode. So, there are 3 you use, and we have the structure like this. Now, as I said, again, I do not want you to kind of memorize them right away, but it will become clear when we study the structure of these terms, and they are very useful. So, this is where we will understand how energy is flowing from one Fourier mode to other Fourier mode, or how kinetic electricity is flowing from one Fourier mode to another Fourier mode. Okay, that is why we labored on deriving these equations very, very carefully. Okay. So, this for kinetic electricity, and we will visit them when we want to derive the formulas for energy transfers and helicity transfers and so on. So, about entropy. So, entropy by definition is omega k squared mod. Now, helicity is the only thing where you need to be careful, it is u dot omega star, but this is omega squared. So, it is just mod omega k squared. Okay. Okay. So, this is what you got, omega k squared. Now, we can write down time derivative of this. So, take the time, so d by dt of this, and in fact, you should do it there, but it is exactly same. So, you do not need to do twice, and replace omega dot by what we derived in the second slide. So, we get this form. There should be one more, yeah. So, there should be two of them. So, k dot u q omega p omega. So, there, in fact, if you see the structure, 2 omega the dot product here, and here u in dot omega dot product. Okay. Now, okay, so there are differences. So, omega dot omega, here this u dot omega, okay, and they mean something. There are, so just to tell you, which we will derive later, just to make you excited about this. So, this term means that vorticity is basically this vorticity to vorticity transfer. So, this is just omega to omega transfer. So, this is energy transfer from one omega mode to another omega mode. This is the term where u to omega transfer, kinetic energy is supplying to omega. So, which term will stretch the vorticity field, first one or second? Second term will stretch, because u is stretching the vorticity field. So, the second term is the stretching term, and first term is in fact is transport of omega by this u. So, these are interpretations one can make by looking at the structure, and similar interpretations work for magnetic field as well. So, these are transport of magnetic field by the velocity field, but this is stretching of the magnetic field by the velocity field. It will exchange among themselves. but overall if you look at the whole field, omega squared will not change by these interactions, but these interactions omega squared can change because u is supplying to omega. So, stretching, yes, we need to worry about it later. So, which ones interact? In fact, so we make, in fact, yeah, so a very good question. So, we have vector k and then they are interacting with p and q, right. So, p plus q is k by convolution theorem. So, now given k, I can have many possibilities of p and q. So, if I change the color of this, how do I change the color? Well, anyway, I will use the same. So, I could have p q like that, p q. So, in fact, there are infinite possibilities, and some contribute more, some contribute less, and that is an important question is called locality. So, which modes, if the neighboring modes contribute, then it is called local interaction. If the far away modes contribute, then it is called non-local interaction. Okay. So, that we are not ready yet, I mean that requires more work.
So, intuitively what it seems is the nearby modes should interact more.
Not that is you can't quite say from whatever we studied so far. Okay, that has to be computed. Okay, and this is coming from force. So, and this viscous term. Okay. So, entropy is also dissipated by viscosity, and that is the term. And these terms are straightforward, but I want you to derive it yourself, just to get familiarized with them. Okay. So, this ends my discussion on derivation of helicity, entropy, vorticity. Okay. So, we stop. Thank you.